In this class, we study conservative force. Conservative force is very important in physics. As soon as we learn the concept of kinetic energy, we find that kinetic energy varies depending on the force. And the relation between the change in the kinetic energy and the work done by a given force is the work kinetic energy theorem of Coriolis. That is the change in the kinetic energy and the amount of work during the motion. From here, we find work subtracted by kinetic energy difference is zero. So we can write it, the change in kinetic energy, difference of the kinetic energy and work done by the force is zero. Here we introduce potential energy, that is negative of the work. Then the expression becomes a simpler sum of kinetic energy and potential energy. It's not changing, it is invariant. This is called the conservation of total mechanical energy. This T and U, this is kinetic energy, and this is called the potential energy. And this is sum is called the Hamiltonian. More correctly, Hamiltonian is p squared over 2m plus potential energy. And this is expressed in terms of coordinate, and kinetic energy is expressed in terms of conjugate momentum. The Hamiltonian is called the total mechanical energy. Total mechanical energy is the Hamiltonian. Hamiltonian is the kinetic energy plus potential energy. This is invariant. So conserved. That's the reason why we study conservative force. If a force is conservative, then the total mechanical energy, that is a sum of the potential energy and kinetic energy, that is the Hamiltonian, is invariant with respect to time development. And when this kind of conservation happens, that's the problem. This is the answer. We call the force is conservative if the work done by the force from a position A to another position B is always the same, independent of the path. This is a C, A to B, C, this blue path, and this red path, they are different. Although the paths are different, the answer, the work done by the force along the path is independent of path. So conservative force is the force whose work is independent of the path. But the reason why we use the conservative is the total mechanical energy is conserved. Work along a closed path always vanishes. If the path in this path, these two paths are different, however, the initial and final positions are the same, they are the same. And what happens if I flip the direction of the one of the two paths? Then the integral is f is constant for any fixed position, but dx is opposite. Here dx, and at the same place, the path of the other one becomes minus dx. So we have negative sign on it. So this one can be expressed as sum of two parts along this path, A to B. And the other part is B to A, C prime. But if I flip the direction, what I have is negative sign on it. So the work done by the force along the closed path C can be expressed as the sum of the work along the path C from A to B and plus B to A. But if I flip the direction of the above path, it acquires negative sign. I have negative sign. But we know A to B, regardless of the path, the values are the same. That is conservative. So because they are the same, they cancel exactly to have 0. As a result, along any closed path, conservative force that does not work at all if we return to the same place to complete a single, well, or double and then multiple as far as the closed path is satisfied. For example, this one, 0. This one, 0. Any closed path. Along any closed path, conservative force does not work at all. Definition of the potential energy and the total mechanical energy. The definition of potential energy is already explained. So the work done by a force can be computed in such a way it depends on the only at the end point some function. After integration we find some function and evaluated at the point B and subtracted by the function evaluated at point A, starting point. As I already told you, the work is the difference in the kinetic energy. However, this one is conserved, but T plus U is conserved if we set U equals to minus W, right? So we have to flip the sign relative to the work. So flip the sign, then it becomes a negative sign of difference of the potential energy. Using this one, moving this negative sign, you will find xb minus u of xa equals minus f dx. This is work, minus work. Suppose that XA is a reference point, X0, and arbitrary point, XB, then you find potential energy at any point is potential energy at a certain point that is constant minus work from the reference to that point. So this is the way to compute the potential energy. As soon as we define the potential energy in such a way, the total mechanical energy, that is Hamiltonian, this is total mechanical energy, is conserved independent of time. So at point A, at point B, the sum of potential energy and kinetic energy is always the same. Next, we consider turning point. Because the total mechanical energy is conserved, the kinetic energy is total mechanical energy subtracted by the potential energy. But kinetic energy is expressed as 1 mv squared. And Cartesian component can be used to evaluate this one to be x velocity, y velocity, z velocity squared sum. So everything is non-negative. Therefore, it is a non-negative. This is the curve of potential energy. The red line stands for the total mechanical energy. Because of this, U, potential energy, cannot be greater than the total mechanical energy. This is the point where the total mechanical energy is less than the potential energy. That means that T is negative. T is negative. T is negative, impossible. So it is a forbidden area. Forbidden area. Except that this is allowed region. This is T is greater than 0. And the boundary, these 2 points, are T equals 0. T equals 0 is x dot S0 vector. T equals 0. So these 2 points are called the turning points. In classical mechanics, this is absolutely not allowed. However, in wave mechanics or quantum mechanics, that is allowed. In classically allowed region, wave appears. In the forbidden region for the classical mechanics, in quantum mechanics or wave mechanics, the wave decays instead of exactly 0. If the potential energy decays to reach the point less than the total mechanical energy, then the wave decays but oscillate again in that manner. So this forbidden region is forbidden only for the classical mechanics for a point particle. In wave mechanics, forbidden region is not absolutely forbidden. There's an exponential decay happens. Reading off force from potential energy is also possible because we find the integral. After evaluating the integral, the upper bound is a free variable x. Then we can take the derivative to find out the integrand again. This is a trick. So this is negative of potential energy. And if I take the derivative, what I get is the force along that direction. This is true for the 2 or 3 or 3 dimensions. We can extend this one to additional pieces. We can find potential energy increases. So this is the slope, a negative value of the slope. Negative value of the slope is the force. So this slope is positive and force is negative. Slope becomes 0, force becomes 0. Slope becomes negative, force is minus slope, so it is increasing. If I flip the sign of the potential energy, is a kind of potential well, the force can be read. Reading of the force from potential energy in 2 dimension, extension 2 dimension is straightforward. Again, the 3-dimensional extension is also possible. Sure, in that case, the potential energy should be the function of x, y, and z altogether. In here, x component of the force, and y component of force are the partial derivative with respect to x and partial derivative with respect to y, and put the negative sign on it. If we want to extend to 3 dimension, it should be fz, something like that. Because it is a vector, force is a vector, this is x component, y component, and z component. They are added, but after being multiplied to the unit vector along the Cartesian axis. So it is convenient to define the operator. Partial derivative is the component of each Cartesian basis. So x component is x derivative, y component is the y partial derivative, and z component is z's partial derivative, is called the gradient. Gradient shows the slope, a vector. For example, in 2 dimensions, we will see the concept plot how to interpret the physical meaning of the gradient on the next page. Anyway, this operator gradient is used for the 2 or 3-dimensional case. In a single dimensional case, I used the minus partial derivative, but actually it is general to write partial derivative minus and then multiply the unit vector along the x-axis. This is the correct way to describe the force in 1 dimension. This is a useful example to understand the gradient and the force coming from a given potential energy. This is the plot for u of xy. This is x and this is y. This potential has a peak at this point, and there is a dip in this point. So the gradient shows how the slope is directed to. So at this point, slope increases as we go this direction. So when we find the equipotential surface, this is the equipotential surface, we'll find a kind of circle or ellipse. These are the equipotential surfaces. And the gradient is heading toward from the lower potential to higher potential. This is gradient. This is gradient. However, the force is minus gradient. Minus gradient. That means minus gradient is opposite to the direction of gradient. So minus gradient means from the higher potential to the lower potential. So it is just like if you pour some water, what happens? Water flows down from the higher potential to a lower potential. Aha. The direction of water flow represent the direction of the gradient. Okay, this is the contour plot for the equipotential surface. The same potentials. U increases, and in this direction, U decreases. This is the direction of a gradient U, and this is the gradient. This is the direction of minus gradient U. So in here, gradient diverges. The force diverges from this point. You can see at this point, force diverges from this point. And in here, gradient is diverging, and minus gradient is the force that is converging to this point. You will find the minus gradient force is going into the point. This is the minimum point. So extracting force from the potential energy in 3D, I have already explained everything. The force is the derivative of integral for x, y, and z. And the work, this is the work, and gradient is a negative of work. Therefore, if I combine everything all together, what I have is a minus gradient applied to the potential energy. So F force is minus the gradient of potential energy. Let's consider the case explicit potential energy form is Gaussian form. Here we have x squared, y squared, z squared divided by a squared. Certainly, exponential something, dimension of something should be dimensionless. Mass, length, time, that's power. This power must be 0, 0, 0. So if I want to compute the force, what I have to do is to compute the gradient. But in this case, this x squared is just r squared. And r is a square root x squared plus y squared plus z squared. This gradient u is a minus e1 hat, x partial derivative, e2, y partial derivative, e3, z's partial derivative of u of r. So what I need to do is x derivative of u of r. X derivative, because it is a function of r only, so we can apply the chain rule. And what happens to r's x derivative? This is square root 1/2, and this is 1/2 minus 1/2 r. Oh, r squared, or x squared, y squared, z squared. So this is 2r, and if I take the derivative, this is 2x. Therefore, it is x over r. In a similar manner, I can find it. It is x over r. Oh, this is y over r. Z over r. All right. So what I find is this one is here, x over r, and round r e to the minus r squared a squared. So x over r, if I take the derivative, a squared minus 2r. Exponential minus r squared over a squared. So r cancels, minus 2x a squared e to the minus r squared a squared. In summary, force is a minus gradient u, so I put negative sign on it, negative, negative, positive. E1 hat a squared 2x, E2 hat 2i, E3 hat 2z, e to the minus r squared over a squared. If I can simplify this, 2 over a squared e to the minus r squared over a squared, and everything all together, this is x vector, or 2r over a squared e to the minus r squared over a squared er hat, because x is er hat r. Okay, this is a way how to compute the force if once you know explicit functional form of the potential energy. Total differential of a multivariable function. So gradient is very useful to find the change of a function depending on many variables. For example, f of x differential is total derivative the same as partial derivative for a single variable function. This is the variation, total differential of a single variable function. X and y, it varies depending on x and y independently. So just to copy this one for the single variable and the x, and the other contribution is a y. Here, partial derivative of x means f of x plus delta x, comma y, f of x y divided by delta x, limit x goes to delta x goes to 0. That means keep y invariant, only vary x. Y's partial derivative is delta y goes to 0, delta y. In that case, keep x invariant. Alright, so in such a manner, I can compute the total differential of this function depending on all of the independent variables. So in such a manner, I can extend it to n variables total differential of n variable function must be its a partial derivative with respect to the first one and multiplied by the differential of that variable, partial derivative of the next two and multiplied by the differential of that variable, and until at the end of the day. Now, it is just a scalar product. Why? So there is a row vector and there is a column vector. Okay, so this is a Cartesian component representation of the scalar product. So this is a gradient of f dot dx, extended to the n-dimensional Euclidean space. If I want to take the time derivative, then what I need to do is just to multiply 1 over dt. Then it becomes the time derivative, and it becomes a whole. These becomes a derivative with respect to time. So this one shows the multivariable case chain rule. Multi-dimensional generalization of chain rule. All right. Because F equals minus gradient potential energy for the conservative force, F dot dx equals minus gradient U dot dx, that is minus total differential. Just what we have done is E1 hat E2 hat y, E3 hat dot E1 hat dx, E2 hat dy, E3 hat dz, that is dx, dy, and dz. And this is total differential. As long as x, y, z are complete set of independent variables determining the potential energy. As a result, this one shows it is just already integrated. The answer is a u, and substitute that b and substitute the position at a. That's it. That's the reason why if the force is expressed in terms of gradient potential function, then that force is also conservative, independent of the path. A very interesting theorem called the Stokes theorem states that once you know the force, you don't have to find out the potential, just compute curl. If the curl is vanishing, then you can say, oh, this force is the work done by this force is independent of path. This one we say E-rotational. E-rotational. That means if it is non-zero, then it is rotational. Rotational force? No, it is not usually conserved. If it is E-rotational, absolutely right. F is conservative. The special version of the Stokes theorem in two dimensions is called the Green's theorem. And at the end of this lecture, you will find the self-test, and you can prove the Stokes theorem as well as the Green's theorem. Stokes theorem, if you want to prove the Stokes theorem, then you have to understand what the left-hand side and right-hand side means. First of all, you want to compute the curl of a vector field. Curl is just like a cross product. We have Leibniz-Civitas symbol. For example, cross product is expressed as E1 hat, E2 hat, E3 hat. Now you have derivative, x derivative, y derivative, and z derivative, and ax, ay, and az. And compute the determinant. This is the answer. So E1 component is the determinant of y and z derivative of ay, az. E2 component is the derivative of g, x, az, ax. And E3 component is a x derivative, y derivative, x component, y component. This is the answer. If we expand this, determinant ABCD equals AD minus BC, right? So first component, y component, 2, and z component, y derivative of z component, and z derivative of y component, and so on. Again, complete version of the proof can be found in Y12, Divergence Theorem and Stokes Theorem in KPOPE Guide for General Physics 2. So if a force, curl of a force is 0, then we say E rotational. And Stokes theorem is a curl, dot product, surface area over a surface. Then that value is the same as the line integral of the scalar product. This is work. Work along a closed curve. Closed curve. This circle means closed. S is a surface, simply connected surface. Then the boundary of this one represents the boundary. Boundary of S is closed. Closed surface. So integral over a closed curve. We put a circle on it. If curve is 0, this integrand is exactly 0. So it is 0. Oh, this work done along a closed path is always 0. Okay, in that case, it is conservative. If it is conservative, total mechanical energy, that is a T plus U, kinetic energy plus potential energy, it is invariant. Any place, any time, this one is invariant. So this is a very, very strong condition. As soon as you compute the curl and the curl is identified to be 0, then the force F is conservative. Any central force is conservative. Okay, any central force is of the form. What is ER? ER, unit vector, is x vector divided by its own magnitude, and magnitude is called R. Any force, okay, there's the origin, and there's a particle, position vector, and ER hat is along this direction, either parallel to ER or anti-parallel to ER. This kind of force, and depending on the strength depends on the radius, and the direction is along the radial direction, then we would say it is a central force. And we find any central force curve is vanishing. Therefore, any central force is conservative. What kind of field? What kind of force? Gravitational force and electrostatic force called Coulomb's law of force. Both of them are central and both of them are conservative. If it is conservative, there exists a potential energy. And the potential energy is independent of the path, and it depends only on the position. And work done by this conservative force independent of position, and work done by the conservative force along a closed path is always vanishing. Why? Let's do the calculation directly. It is necessary. So, the unit vector along the radial direction is written in this form, and you'd like to compute the curve of the force in case if it is a central force. Let us compute the trivial partial derivatives. X to x is 1. Y partial derivative with respect to x, it vanishes. So for k and j, if they are the same, it is 1. If they are different, it becomes 0. So it is chronic delta. If it is a radius, r, x squared, y squared, z squared, then it becomes 2r, 2x, so x over r, right? What happens to the case x over r derivative? We can take the derivative of x, then we have 1 over r. We can take the derivative of 1 over r, then means x times 1 over r. And chain rule, x derivative, and then this one. So this one is x over r. Combine everything, so with this x squared over r cubed. Okay. So in case we have y over r, everything is the same, except that this y is constant with respect to x. So the answer is minus xy over r cubed. So for any function of r, partial derivative with respect to x is, one can make use of chain rule, and this one is xj over r. Okay, everything is ready. We just compute the curve. Curve can be expanded in terms of Cartesian basis, I, jth derivative, and kth component. So fr and unit vector is replaced with Cartesian vector, then x component to divide by r. So let me combine these two to have a small f of r. So if I take the derivative, J and K the same, then 1. If it is not the case, vanishes. So this part is delta JK, and overall factor is the same. If I take the derivative of this, then I can copy this result. So xk remains the same, and I bring xj over r, right? xj over r. So there is a typo. This 3 should be removed. So I have removed this typo. This is just a single power, and making use of this relation. So anyway, if I sum everything all together, keeping I fixed for a single I runs from 1 to 3, I need to carry out the summation. Then we encounter sum over j and sum over k. Both of them runs from 1 to 3. And we have epsilon ijk, delta jk, and epsilon ijk, xj, xk. These two kind of sum. In this sum, I have j and k symmetric on the exchange, and I have j and k anti-symmetric on the exchange. So, for example, epsilon 1, 2, 3, and the delta 2, 3 appears in the summation, and epsilon 1, 3, 2, and delta 3, 2 appears in the summation. When they appear in the same frequency, so they are combined as the sum in the summation. However, delta 2, 3 and 3, 2, they are the same. So delta 2, 3 is factored out as a single, just one. Then we have epsilon 1, 2, 3 plus 1, 3, 2. This is minus 1, 2, 3. So epsilon 1, 2, 3. So in the summation, this is 1, and this is 1 minus 1 equals 0. So in this manner, any term exchanged, j and k exchanged frequency, because summation is symmetric, this part is anti-symmetric under exchange of j and k. This side is this factor is symmetric on the exchange of j and k. This one vanishes exactly. In the same manner, instead of delta 2, 3, we have xj, xk. So in this summation, we have x2, x3 is factored out, and epsilon 1, 2, 3 plus epsilon 1, 3, 2 appears. This is epsilon 1, 2, 3 minus epsilon 1, 2, 3. This is x2, x3. x2, x3's coefficient is 1 minus 1 equals 0. So every term for I runs from 1, 2, and 3. So any component, E1's component, E2's component, and E3's component of vector vanishes exactly. Therefore, the car is vanishing. So as a result, any central force is irrotational. Irrotational. Car central force is 0. If the curl of the force is 0, then I can write it as in this form, surface integral. Because this one is 0, this one, whether this one is 0 or not, we can always write it as a work over a closed path that is the boundary of this surface. But however, this is irrotational, it is a 0. So for any path, this one is vanishing, that means it is a conservative. There are examples of a non-conservative force, damping, friction. This kind of force does not return the energy to the kinetic shape of the kinetic energy. It has been distributed over uh, a bulk body. Uh, the body has a lot of particles, and they actually their kinetic energy cannot be returned uh, to another form. So it has been distributed to many particles. So I cannot control. I cannot pay back. So that does not mean energy is not conserved. The distributed energy cannot be controlled to return. So conservative force does not mean non-conservative force uh, is non-conservation of energy. Conservation of energy is true. However, I cannot return the kinetic energy that I want as I wish. However, for conservative force, if I return the particle to the same position, I can always get back the kinetic energy. That's the difference. So in the later part of this lecture, not this lecture in the series of lecture, X series, we will study thermal physics and we study the viewpoint of the statistical mechanics to interpret the thermal physical behavior. So generalized conservation of energy is not only for the mechanical energy, total mechanical energy that is the sum of the kinetic energy and potential energy. There is another kind of energy saved in some form that is thermal, either thermal or internal energy. Okay. Always, if you encounter some new mechanical variable, physical variable, you are advised to analyze the dimensional structure and look for useful SI units. Self-test. This one we mainly consider the Stokes theorem. The Stokes theorem is useful to identify the conservative force. By computing the curl, we can, in most cases, we want to verify a force is conservative. So the best way is to compute the curl. And if the curl is zero, that is irrotational, then force is identified to be conservative. Once it is conservative, then it is straightforward to consider the conservation of total mechanical energy. Again, we recall the definition of a curl of a vector field with the determinant form, a derivative, and components. Okay? Consider a surface integral. This surface does not have to be on the xy plane. It is for example, a curved surface. That's fine. So what we'd like to do is just divide this one into many beams in the XYZ space. So in that case, the surface becomes a combination. This surface S can be approximately the same as the sum of the faces of cube. Many faces of cubes distributed over the space put many cubes with a very small size. And then we can approximate this total surface as the sum of the faces of the cubes. And let me simply consider a single cube calculation first, and then at the end of the day we can combine the logic for the many cubes to cover the whole area of the arbitrary surface. Then the integral what we want to compute is the curl of a vector field over the surface. And I told you this surface can be decomposed into many pieces, very tiny one. And then as in reverse, the number of surfaces, subsurfaces, partial surfaces will be increasing to infinity. And then each small surface can be decomposed into three pieces. That is normal to the E1 and normal to E2 and normal to E3. Three different spaces. And if we substitute this one to the differential of the integral, I phi, this is proportional to E1 and this is proportional to E3, and that is coupled to the curl of the third component. In a similar manner, E2 component and the E1 component can be added together. So let me consider this part first. That is perpendicular to z-axis. So that is on the xy plane. The double integral, this double integral can be parameterized for this and for this because this is integrated over x and this is to be integrated over y first, then it becomes very simple. So first integral can be parameterized by, because there is a derivative with respect to x, I would like to integrate over x first. And the second one, I have derivative with respect to y, so I want to integrate out y first. So in the first case, integrate this x first. Integrate x first. So integrate from x minimum to x maximum in this way. And outside this integral will be over y. So over y from y minimum to y maximum, and for each given y there is x minimum depending on y, x maximum depending on y. So substitute the integrand, this integrand here, x is integrated out, and what I have to do is just put this ay, but evaluate it at the maximum value of x, evaluated in here, and subtracted by these values evaluated on the curve of minimum values of x. So if I carry out the y integral in here, these maximum points from y minimum to y maximum, these maximum points becomes the border C plus. And then we have minus x minimum, this part, from y minimum to x maximum, from here to there. That is opposite direction of this. So minus from here to there means a plus from here to there. this direction. Therefore, this difference is actually the sum. This is sum. That is integral over closed curve. So closed curve C. In a similar manner, the other integral is also integral over the closed curve. The problem is that this one is integrate over dx ax, and this part we have dy ay. And actually, the sum of these two contributes to the third term. The sum is this one, line integral over closed path on the xy plane. In a similar manner, yz plane and zx plane, we can do the same job. Finally, if you combine everything all together, you will find that the curve integrated over the surface as a scalar product with the surface element. It results in whatever shape it may be, your integral is reduced to integral over closed path. And what I'm interested in is a vector field A is a force, and this force is of the form. This one contributes to work done by the force on a closed path C. Therefore, if curve is zero, that is F is irrotational. In that case, the left-hand side vanishes. Therefore, the work is vanishing for any closed path. That is the definition of the conservative force. Okay, so the irrotational field is conservative. Irrotational force is conservative. Is very, very important and useful. That's it for today.